Ramen, the staple food of college students and those looking for a quick and easy meal. But out of the various flavors, brands, and styles of ramens out there on the market, how do people make their choice? Is there an underlying pattern to explain it all? This is the question we will set out to answer today. But why should you care about what makes someone buy ramen? Well, we have a few suggestions. If you're a business looking to sell ramen, it'd be very informative for you to know about what attributes to carefully select and choose in order to maximize customer delivery. Or perhaps you're simply a ramen connoisseur and want to keep an eye out for what tends to make ramen better or worse. This analysis was performed by John, Theo, David, Richard, and Nicholas. The data used in this analysis was taken from theramenrater.com, where there are over 3,000 ramen ratings of different ramen noodles eaten by only one person, known as the ramen rater. For ramen selection, we wanted to stick with things that would be specific to the ramen itself and not necessarily what it was associated with, so we stuck with the attributes variety and style, and we were trying to predict stars, how good the ramen was.
In order to clean the data, we removed all NA values. The ramen names were made lowercase and the top category was removed since it was mostly NA values. Also, these unique values in the star category were shown. Some of them were removed, of course, because they were either a fraction, too large, unrated. Anything that wasn't between 0 and 5 was removed. As you can see there, as the reviews progressed, the ratings in stars stayed pretty distributed, so we could tell that he was pretty unbiased over time. We created a word cloud based on the names of all the ramen. The variety attribute, which was the names, was used to create a word cloud, but the most popular words were removed. These words were noodles, noodle, ramen, instant, flavor, and flavor. And that's just because we believed that these words didn't really separate any type of ramen from each other. They were just kind of universal. So the final word cloud was on the right, with some of the most popular words being spicy, soup, beef, chicken. So in order to continue with creating a model for this data, we created a binary attribute for some of the most popular words. For instance, in the top row, you see that the variety contains the word beef, so that would obviously be true on the right there for the binary variable. In addition, our group also collected data from Wegmans. We visited a local grocery store and collected name, brand, type, and country of origin of different ramen types. 15 different data points were collected, and this data was just used to see what star ratings these ramen could possibly receive based on the data set.
In order to continue our data exploration, we thought that k-means might yield some interesting results. So we plotted the number of keywords. Now that's the sum of the one-hot vectors, which are containing a 1 for a certain word or a 0 for that certain word, against the star rating of that ramen containing the keywords. Now, as you can see, there's no real discernible clusters here, so the k-means was not too useful for analysis. We also looked at the distribution of star ratings, noting that there is a concentration of ratings of 4, which might skew our later analysis.
So one of the models that we used to analyze this ramen data set was k-nearest neighbor. And this was used to create a model for predicting the stars rating of each ramen type based on the ramen title, brand, the type, and the country of origin. And this essentially was done with using those binary attributes that we talked about earlier, based on the most popular words found in all of the ramen titles. The k-nearest neighbor model was done with cross-validation, and it actually gave a pretty low accuracy, around 48%, which was much lower than what we've seen in class. And this was unfortunate, but some of the possible reasons that this might have happened were outside factors, such as mood, appetite, etc. of the rater while he was eating this ramen. And also the fact that some of the ratings had to be rounded to the nearest whole number. So for instance, if the person had given a ramen a rating of 4.2, and that was the only 4.2, that had been rounded down to 4 for a little bit of less accuracy. And the confusion matrix for our data was seen on the right as a visualization of this data. So we also use this model to do k-nearest neighbor on the Wegmans ramen that we actually collected. So we inputted all of the attributes of this data. As you can see, I've shown the variety of this data and the suggested rating that the model had spat out. For instance, the first one, garlic and vegetable instant rice noodle soup, got a rating of 5 stars based on this Kaggle data. And the Ansong noodle soup, beef, and fermented bean got a rating of 0 stars. In addition, K-nearest neighbor was ran without cross-validation, just out of curiosity. Without the cross-validation, it was looped through various Ks to see what the optimal K was for the accuracy. And the optimal K turned out to be 3, which was a lot lower than the K with the cross-validation. And this, of course, was expected because the K-nearest neighbor model had more of a fit for seen data rather than the unseen, which was accounted for with the cross-validation.
As we didn't have much success with k-nearest neighbors, we also tried logistic regression to model our data. Now, because logistic regression is a binary classifier, we had to modify our data a little bit. So we created a new attribute, class_stars, that was 1 if the rating was more than 3 stars, and 0 if the rating was below 3 stars. Then we applied a logistic regression using cross-validation to find the best parameters, and we get the confusion matrix on the left here. When you look at the model, you see that the accuracy is around 82%. Now this would be good, but when you look at the confusion matrix, you see that the model is predicting almost all true. This is probably because the attributes are not differentiating the ratings from each other enough, and as a result, you get a very one-sided prediction, which is not too useful in this case. And due to the poor results, we took our analysis to the naive Bayes model. Now, in this case, we could go back to using classification for all 5 ratings as opposed to just above 3 or not, but it suffered from a similar problem with attributes not being distinct from each other enough to actually separate the ratings. And as a result, naive Bayes also only predicted 1 value, in this case being 4 stars for all the reviews. And as a result, you got an accuracy about 52%, but that was only due to the prevalence of 4-star ratings with rounding. So we continued our classification efforts, this time choosing to create models using decision trees and random forests. However, the old problems cropped up again. When we tried to train a decision tree with style and the one-hot vectors created from the variety titles. As a reminder, the prevalence of words like soup or chicken, the decision tree modeling process actually chose to ignore all of the one-hot vectors due to them not providing enough information gain, and only chose to use the decision tree based on aggregating style into different groupings. As you can see here, there's only one decision being made. Is the style a bowl, cup, packet, restaurant, or tray? Or is it not? This is a marginal improvement from naive Bayes and logistic regression, so we went forward with a random forest model. You can see that in training sample results in the top right there, with a normal decision tree and using a random forest, with cross-validation to train different parameters and tune them. And when we got the best model from training, we applied it to the test data, and that's what you see in the bottom left with the confusion matrix and the accuracy. So in summary, the accuracy did improve. However, we're still getting predictions that are centered around 4, this time going a little bit into 5, but still not the spread that we would like to see.
Since most of our data wasn't in a numeric form besides the ratings, which was out of 5, I had to change the styles, such as whether the ramen came in a pack, bowl, tray, or cup, into its numerical value. So the first step was I went online and I found out how many grams are in a pack, bowl, cup, and tray, and created a new column to store those values.
However, unfortunately, when we plot these values against the star ratings, there appears to be no significant correlation, and thus linear regression on just these two variables does not seem like a very strong choice. And as you can see, the R-squared value for that linear regression was not very descriptive of the data. However, we went forward and created multilinear regressions with the milligrams and all the one-hot vectors of variety words. And as you can see, that R-squared value indicates that that model was more descriptive of the data. Not very descriptive, as it's a very low R-squared value at 3.5%. However, there is some description being captured there. Moving forward, we tried turning the ramen type from milligrams into more one-hot vectors, and doing a linear regression on all these one-hot vectors created an R-squared value of 4.5%. So what is the takeaway from this analysis? Well, unfortunately, in this case, the result is that these attributes were not very descriptive of the ramen and not very helpful in predicting the rating value. However, this is okay because both the null and the alternative hypothesis are good to find out. For businesses, we would suggest creating more attributes for your data, maybe internal taste tests or ingredients used to predict your ramen success better. And for ramen connoisseurs, we can safely assure you that the information found on the packet of ramen is not quite enough to inform you of the taste, so we encourage you to continue going out and trying fresh and new ramen brands. That concludes this analysis. Thank you for watching.